Have you ever stopped to think about how we can send a probe to Mars with pinpoint accuracy or build a bridge that stands for a century? Well, it all goes back to a revolution that happened over 300 years ago, and it's all thanks to three, believe it or not, pretty simple laws of motion. Today, we're going to unpack how those laws completely rewrote our understanding of the universe and literally built the world we live in. This right here, this was the dream. This was the big idea that Newton's work kicked off, captured perfectly by the mathematician Laplace. He imagined this perfect clockwork universe. The idea that if you could just know where every single particle was and where it was going, you could predict the future, forever, with total certainty. And that's the big question that's going to frame our whole conversation. Newton's laws gave us this incredible power to predict things on a scale no one had ever even dreamed of. But, and this is the really interesting part, they also held the secrets to their own limits. They showed us a universe that's way more complex, and frankly, way more interesting than just a simple machine.
Okay, so to really appreciate what Newton did, we have to take a step back and look at the world he was born into. Because before his laws, trying to understand motion wasn't really about math, it was all about philosophy.
For hundreds of years, Aristotle's ideas were the law of the land. In his view, motion was about, well, an object's purpose. A rock falls because its natural place is down on the earth. An arrow keeps flying because the air is supposedly rushing around to push it from behind. The key idea was, if you want to keep something moving, you have to keep pushing it. It's a way of describing the world, for sure, but there's one huge thing missing. You can't calculate anything with it. There was no real predictive power.
And into this world walks Isaac Newton. And he doesn't just offer a new idea. He basically provides a whole new operating system for reality. He wrote the source code for motion. And here they are, the famous three laws. The first one, inertia, is pretty intuitive. Objects just want to keep doing what they're already doing. The second one gives us the math for how forces change that motion. You've probably seen it as F equals ma. And the third law, action-reaction, points to this really deep symmetry in the universe. Forces never act alone. They always come in pairs.
Now, this is a fantastic question, and you might be thinking it right now. I mean, if F equals ma, and you set the force F to 0, then acceleration A has to be 0, which means velocity is constant, which sounds exactly like the first law. So is the first law just extra? Unnecessary?
Well, not so fast.
See, the first law isn't just a special case of the second. It's more fundamental than that. Think of the first law as the rule book. It sets up the entire game. It defines the specific conditions, the specific viewpoints, from which the second law even works properly. It tells us how to find something called an inertial frame of reference, which is the only place where the math actually holds up.
So what is an inertial frame? Put simply, it's a point of view that isn't accelerating. Imagine you're on a train moving at a perfectly smooth, constant speed. If you put a coffee cup on the table, it stays put. You're an inertial frame. But the second the train lurches forward or hits the brakes, your coffee cup slides. Now you're in a non-inertial frame. The first law is the test that lets us find those good, non-accelerating frames where F equals ma actually works.
Okay, so with this incredibly solid, logical foundation in place, Newton was ready to do something that no one had ever done before. He was ready to use these laws to unlock the secrets of the entire cosmos.
And this is just, it's beautiful. This is the power of the system in action. You see, for years, people like the astronomer Johannes Kepler had figured out that planets moved in these weird oval shapes called ellipses. They had the observations, but nobody knew why. Well, Newton took his laws of motion, combined them with his law of universal gravity, and boom, he was able to derive the exact shape of those orbits from scratch. He turned what into why. I mean, you can't overstate how huge this was. This was the moment physics went from being a kind of philosophy that just described things to a hard science that could predict things with incredible mathematical accuracy. The motion of the planets was no longer some deep mystery. It was a math problem, and for the first time ever, we could solve it. And this foundation was so solid that later physicists didn't have to tear it down and start over. They built right on top of it. You might hear about things like Lagrangian or Hamiltonian mechanics. These aren't really new physics. They're just more advanced, more powerful mathematical toolkits built on Newton's ideas, designed to solve even trickier problems.
So this newfound ability to predict the world didn't just stay up in the heavens with the astronomers. It came right down to Earth and kick-started an engineering revolution that is still going strong today. Seriously, just look at this list. The applications are everywhere. Every single time we launch a satellite into orbit, we're using Newton's laws. Every bridge you drive over was designed by engineers calculating forces, which is pure Newtonian mechanics. The shape of an airplane wing, the path of a rocket. It all comes back to these three simple laws.
And it gets even more personal than that. Think about a field like biomechanics. Engineers use these very same principles to understand how the human body moves. And that knowledge is absolutely crucial for creating devices that help people in physical therapy or for designing tools that improve the quality of life for the elderly. We're talking about 300-year-old physics driving cutting-edge medical tech. It's amazing.
But the story doesn't end with a perfectly predictable universe. That beautiful dream of a flawless clockwork machine, well, it started to show a few cracks. And the fascinating thing is, those cracks were found not by proving Newton wrong, but by pushing his laws to their absolute limits. And here's a fantastic twist. Newton himself actually suspected that the solar system wasn't perfectly stable in the long run. He noticed these tiny little wobbles and deviations in the planet's orbits, and he figured that over huge amounts of time, they might just add up until the whole system needed a reformation, as he put it. Maybe even a little nudge from a higher power to set things straight.
He was really onto something. See, the sun's gravity is obviously the main force in charge, but every single planet is also pulling on every other planet with its own tiny bit of gravity. On their own, these forces are minuscule. But over millions and billions of years, all these tiny, complicated tugs of war add up, creating what's known as the many-body problem. And it is incredibly difficult to solve. So with the power of modern supercomputers, we can run simulations to see what happens over these vast timescales. And what we find is the clear signature of something called mathematical chaos. This is the wild idea of extreme sensitivity to initial conditions. It means that a change so tiny you can never even measure it, like literally the gravitational effect of moving a pencil on your desk, could be amplified over 1 billion years to cause a huge change, like whether Jupiter is on one side of the sun or the other. So what does this actually mean in practical terms? Well, these simulations tell us there's about a 1% chance that Mercury's orbit could become so unstable that it actually collides with Venus sometime in the next few billion years. So yeah, the clockwork has a little bit of a wobble in it.
Now, it's really, really important to understand that chaos is not the same thing as randomness. The solar system is still following Newton's laws perfectly. It's completely deterministic. The unpredictability comes from the fact that you could never measure the starting positions of everything with enough precision to make a reliable long-term forecast. The uncertainty is baked right into the rules of the game. Which brings us all the way back to Laplace's beautiful dream. It's still this incredible vision of a deterministic universe. But what chaos theory tells us is that even if you knew all the laws perfectly, perfect prediction is impossible in the real world. The universe is just more subtle, more complex, and frankly a lot more interesting than a simple clock.
And that, really, is the ultimate takeaway from the Newtonian revolution. It gave us these godlike powers to understand and build our world. But it also taught us a really important lesson in humility. It showed us that even inside our most powerful and certain theories, you can find this deep, beautiful, and profound unpredictability. And it just leaves you wondering, doesn't it? Where else in science might we find that? What other things we think are certain might be hiding that same kind of amazing complexity?